we started learning about ionic compounds and thinking about the electrons and how they're lost and gained to form cations and anions. And we spent some time learning how we can predict the charges of the main group elements, those are the tall columns with the A's, using the octet rule. I also mentioned and we saw some of the transition elements and how they can have more than one cation. And then the last thing we were looking at is polyatomic ions, which are groups of atoms that have a charge. So once we know a little bit about ions, the next step is to take those ions, cations and anions, and put them together so that they represent a chemical compound. So we're going to be writing formulas for ionic compounds. Now this first slide has steps that are written down, and I'm going to go over them, but I think what would be good for you to do is just go through them with me now, then look at some of the examples that I'm going to do, and then come back to the rules, or the steps, I don't think they're rules, the steps, and see if they don't make more sense. Because the first time you read these, they may not make sense, but once you see an example, I think when you have that, you'll be able to come back and say, oh, okay, I see what it's talking about. So let's start with step 1. So it just says identify the cation and the anions. So those are the positive charge and the negative charge. So we have to have the two ions. And then just a reminder, metals, it should say form, not from. Oh, I read it wrong. It does say form. Okay, it says the right thing. Metals form cations and nonmetals form anions. So metals are going to be positive ions, for example, calcium. And nonmetals are going to be anions, for example, chloride. And if you are uncertain about ions, I do have some lecture videos that go through ions, or look back at your notes from class, because that's what we were working on in the previous class. Now then step 2 says using the charges. Okay, so we have our ions, and now we're going to use the charges of the ions to determine how many of each ion is needed, and here's the important part, for an overall charge of 0. So I'm going to very basically try to describe what that means, and then in the next slide we're going to do examples. So what the overall charge of 0 is, it means that if all of your cations have a 1+ charge total, and then we want the anions to have a 1 negative charge total, because a positive 1 and a negative 1 would equal 0. Or if all of your positive ions add up to a 3+, and then we would want all of the negative ions or anions to add up to a 3-, and then together those things equal 0. Or another example, there's sometimes all the positive add up to 6+, and then the negative would have to add up to 6-, because 6 positives and 6 negatives equal 0. So we're going to take the charges and we're going to put them in a proportion or a ratio that we have the same number of positives and the same number of negatives. That's the ultimate goal, because our compound has to have overall a charge of 0. Okay, so we're going to use examples, and we're going to do that. And then step 3 says to write the formula, place the cation first. So that's the metal, and this will always be true. The cation or metal will be first, and then the anion will be after that. And so in all of our formulas and in all of our names, the metal is going to be first and the nonmetal is going to be second. And then it says as little bullet points. Oh, wait, before I go there, I always just assume this, but once we push them together to write a formula, then we're not going to write the charges in the formula. Okay, so if, for example, sodium ion is Na plus, and chloride ion is Cl minus. So I would have the example where I have a 1 positive and a 1 negative, and a 1 positive and a 1 negative would equal 0. So the formula becomes NaCl. And so notice I no longer write the charges. It's still sodium ions and chloride ions in the compound, but because their charges cancel, when I write the formula, I don't represent them. I don't show them. So over here, these are what the ions would look like. And this right here is what the formula of the compound is like. And I'm going to do more examples, but I just thought this would help you with the language anyway. So then it says here, use subscripts to show the number of each ion. So subscripts are when we write it below the symbol to make the overall charge of 0. Then when no subscript is written, assume to be 1. And so in this example here, there's only 1 sodium and 1 chloride. And so there are no subscripts because they're both 1. All right, now you could have read through these rules with me and still kind of scratching your head because you're not quite sure what's happening. So we're going to go and we're going to do some examples. And then after you see some examples, it might help you to come back, rewind the video and come back and look at these steps and then see if they're not clearer for you. All right, so I'm going to start with some practice that are all going to have something in common. And I'll talk about that when we finish the 3 examples. Now, what I'm doing first on this periodic table on our slides is I'm writing the charges that we predicted in the previous class using the octet rule. And remember, for the main group elements, that's the tall columns or all the groups with A's, we use the octet rule, and then we can use the location of the element and predict their charges. So for example, I want to start with potassium. So here's potassium, and it would be in group 1A, so it has a 1 plus charge. So that's the ion potassium. And I want it to be with bromide. So bromide as a halogen, it has a 1 minus. And if you recall, the ions for the metals are named the same as the element. Oops, I just saw that I wrote just a 1 instead of the plus. Let me go back. Sorry. And the negative ions, the anions, they change the name of the element by changing the ending to IDE. So this is a potassium ion and a bromide ion. Now remember, in the steps, we wanted to have the charges equal 0. So if I have a 1 plus and a 1 minus, if I put those two together, the charge would equal 0. So to write the formula, it would be KBr. And then to name it, would simply be, when you name ionic compounds, you just name the 2 ions. So I take the potassium, see right here, that's the name of the first ion, and then I'm going to end it with bromide. Try not to make these harder to name than they are. It's just the name of the 2 ions. Now, let me go through, and I want to identify what each thing represents before we go to our second example. So these right here represent the ions. These right here, where I have the little word ion, that's the name of the ions individually. This right here is the formula of the compound. And this down here is the name of the compound. All right. Now, I'm not going to write that for each one, but as I use these words, this is what I'm referring to. Okay, so let's do our second example. So I want to do magnesium. I'm going to choose magnesium, which would be in the alkaline earth metals, and that's a 2+. So the ion is Mg with a 2+. And we name the metals the same as their elements. So this is magnesium ion. And then I want to do this with sulfur. Sulfur is in group 6A, which is a 2-. And then the nonmetals, the anions, we change the ending to IDE. So instead of a sulfur ion, it's called a sulfide ion. Now I want to put these two together, remembering that the charges have to equal 0. So I have a 2+ and a 2-. So they're the same number. So when they're the same number, they cancel out with each other. So I'm going to write it. I need one of each, MgS, because they're going to cancel each other out. So that's the formula of the compound. And then the name would just be taking the two names of the ions. So I would take magnesium sulfide. That's going to be the name. Okay, I want to do one more example, and you're going to see what this example has in common. If we were in class, I'd make you tell me, but we're not. So we'll just I'll tell you, and you can see if you got it. All right, so I'm going to choose aluminum, which is a 3+. And I'm going to choose nitrogen, which is a 3-. Now remember the ions for the metals, we name the same as the element. And the nonmetals, we change the ending to IDE, so this is nitride. Now following along, and hope you're catching on, that you look at the charges to do the formula. And this charge is a 3+, and this one is a 3-. So a 3 and a 3 will cancel each other out, right? Because a 3+ and a 3-, if I put those together, it's going to equal 0. So I only need one of each. So I would write for the formula of the compound, 1 aluminum and 1 nitrogen. And it looks kind of weird, but that's what I would write for those two ions. And then when you name it, remember, ionic compounds, you just name the two ions. So this is aluminum nitride. Oops, okay, I got it. When I change colors, there's always a little pause. All right, so there's 3 examples. Example 1, example 2, and example 3. And what they all have in common is that the charge of the positive ion has the same number as the charge of the negative ion. So there's a 1+ and a 1-, a 2+, a 2-, a 3+, a 3-. And so what I need you to remember is if the number on the cation and anion charges are the same, you will always only need one of each because they will cancel. Now, one reason I start with this is because it's easy for us to see 1-to-1 ratios. And then the second reason I start with this is on the next practice slide, I'm going to do examples where they're not equal. Like it's not a 1 and a 1, a 2 and a 2, a 3 and a 3. And I have a little shortcut to do with those. But if you use the shortcut on these, then you don't automatically get the correct answer. So I want you to be aware that if the numbers are the same on the positive and the negative, so they have the same number on their charge, it's always 1 to 1. Okay? So now let's try some examples where they are not 1 to 1. Okay. So I am going to, again, on the top of my periodic table, write the charges. Okay, I'm going to do 3 examples with this as well. So I'm going to pick, this time I will pick, let's pick way down here, rubidium. And rubidium is in group 1A, so it is a +1. Now, I'm going to pick instead on the nonmetals, I already did I do oxygen? No, I think I did sulfur. I'm going to do oxygen, which is a 2-. Now, some of you, your minds just think in terms of numbers, and you might already be able to see how many you would need of each. Other people, this is harder. It's just how our brains are, and some of us have to work more at one thing than another. So what I'm looking at here is I see this is a 1, and this is a 2, so that would not equal 0. And so when I think about it, I would need 2 rubidiums, right? Because I would need 1, 2, and if I had 2 rubidiums, I would have 2 positives. And then the oxygen, just 1 oxygen would have a 2 negative. And so that would cancel because I would have 2 positives here with 2 rubidiums and 2 negatives. So I would write the formula. Oh, and let me write their names because we're practicing that too. This is rubidium. That's a rubidium ion. Metals are named the same. And then oxygen turns to oxide when it's a negative ion. Okay, so I need 2 rubidiums. RB2, that's the subscript, and I only need 1 oxygen. So notice I'm not writing any charges, but I need 2 rubidiums, so I have 2 positives, and only 1 oxygen, so I have 2 negatives. And then how I would name that is rubidium oxide, because you just name the 2 ions that are there. Now here is the trick. It's not a trick. I shouldn't call it a trick. It's really just a shortcut. It's a mathematical shortcut so you can figure out how many it takes of each to make their positives and negatives equal. It's really just a shortcut. It's something called the crossover method. And what it means is, or what you do, is to figure out how many rubidiums you need. You will cross over and look at the charge of the oxygen. So for rubidium, I look up there and there's the number 2. I need 2 rubidiums. Okay. Then for the oxygen, you cross over and look at the opposite ion. So I would look up here. Now remember, there is no 1 because they don't write the 1s. So I only need 1 oxygen. So if you look down here is the 2 because I need 2 of those. And then I only need 1 oxygen, so there's no number. So it's a shortcut. I'm not moving charges. Like people move charges and then they write charges in the formulas. I'm not moving charges. what I'm doing is when I try to figure out how many of the positive one I need, I look at the charge of the negative one. And whatever that number is, that's how many I need. And then if I need to know how many of the the negative ones I need, I look at what the charge on the positive ion is. So it's just a math. It's just to get a quick way to figure out what number these, how am I going to get the two charges equal? So let's try another example. Okay, so I want to pick let's pick calcium, which is a 2+. That would be the calcium ion. And let's pick iodine, which is a halogen. It would be a 1-. And it's not iodine anymore. We call it, when it's an ion, we call it iodide. Remember, the nonmetals change their ending to IDE. All right, so you can pause it and try to get the formula if you want. I'm going to show you with the crossover how you could think about it. So if I look for calcium, I would look at the charge up here, which is a 1. So I'm going to need 1 calcium in the formula. And then for the iodide, I look at the opposite charge, so the other one, and that's a 2. So I'm going to need 2 iodides. Now, if you're thinking about the numbers, you can think, okay, calcium has a 2+, right? And 1 iodide only has a 1-, so that doesn't cancel. So it needs 2 iodide, so it can have 2 negative, and then it cancels. So that's why we need 2. So you can think about it that way, but I really find when you do the crossover, it's so quick to figure out how many you need of each. And some of them are way more obvious than others. Now to name this one, I would name it with the calcium, because you just name the ions, and then iodide. All right, I'm going to do one more here, and then we're going to try some with the transition metals and the polyatomic ions. They work the same way. So I want to do aluminum, which is a 3+. And I'm going to do sulfur, which is a 2-. Now, if you want, you can pause the video now and see if you can get the formula. This is the aluminum ion. We named the cations the same as the metal. And then the sulfur, when it's an anion, is sulfide. So crossover. For the aluminum, you would look at the opposite charge, the one that it's going to be with, and that says I would need 2 aluminums. No charges in formulas. It's telling me how many I would need. Then for the sulfide, I would look over at the other ion, and that number is a 3. So it's going to take 3 sulfides. Now I want to think about it in terms of charges, just so you can maybe make the connection. So 1 aluminum has 3. And if I had 2 of them, see, that would be 6. 1 sulfur has 2, which wouldn't cancel out with 3. But if I have 3 sulfides, that together equals 6. So when you have 2 aluminums and 3 sulfides, you have 6 positives and 6 negatives. And that's why we have to have that ratio. Now, in terms of naming, we would name the metal first, so that's aluminum. And then the nonmetal, which is the anion, is sulfide. Now notice it doesn't matter that there are multiple aluminum or multiple sulfides. It doesn't matter. In ionic compounds, you literally just name the 2 ions that are present, not how many there are. And so here are 3 examples when the charges are not equal. And we can use that crossover. What I'm saying there, if you can't understand, is crossover. Shortcut. I guess it's a shortcut. It's not a trick. We're not moving charges. It's just a mathematical shortcut. So now I would like to do one more practice. Okay, and I want to practice with some polyatomic ions, and we'll go in and we'll look at some of the, what happens if it's one of the transition metals that can have more than one cation. Now, before we get going, I do want you to know that polyatomic ions and transition metals with more than one charge all are treated the same way as what we've been doing. Okay, so it's not really anything new. The hard thing, especially for most students, is with the polyatomic ions, until you've really started practicing learning them, your brain doesn't see it as a group. It sees it as individual elements, and it makes it hard to try to put it together like you feel used to. So one thing I can recommend is memorize those polyatomic ions that I recommended, because it really will help you in this section. So I'm going to start, and I want to start first. We're going to do one with iron, okay? And iron has 2 charges. It has a 2 plus and a 3 plus. And if you recall, I have not asked you to memorize this. I'm going to give you the chart from your book that has some of the common ones. So you may want to refer to that now as well. And one thing that's different with these is we use a Roman numeral behind the name of the metal to tell you which one it is. The only names that have Roman numerals for what we are working with are cations that have more than one possible charge. So I put iron with a Roman numeral 2 to tell you that that iron has a 2 plus, and iron with a Roman numeral 3 to tell you that that iron has a 3 plus. So why don't we do one with iron 2 to start with? So its name is iron, Roman numeral 2. And let's just go over here and maybe I'll pick this one, which is called nitrate. Polyatomic ion names really do have to be memorized. There are some patterns once you have some foundation and know a few of them. There are patterns, but initially I find that the best thing to do is just memorize a handful of the formulas and names, and then it allows you to start seeing some of the connections. So what we want to remember here is that we're interested really in the charge. So I just highlighted the NO3 because I don't want your mind to get distracted by that. We can still use the crossover. So I can still say iron, how many do I need? And I look not at the NO3, but it's all based on the charge. So if I put these 2 things together, I need 1 iron. And then I look at the nitrate. Now, the nitrate is going to be this whole thing. That's what nitrate is. It's NO3. But again, I don't have to worry about that. How many I need is based on the charge. So I'm going to need 2 of them. Now, when you have a whole group of something and you need more than one of it, in our formulas, we use a parentheses. So I put NO3 in a parentheses. It's like there's the group. We know that's nitrate, and I need 2 of them. So if you need more than one polyatomic ion, you're going to use parentheses to show how many you need. So you'll put a parentheses, and then behind the parentheses, you'll put how many you need. Now we name these no different than we did before. We just name the 2 ions that are present. So this one's name would be iron 2 and then nitrate. Now notice the 2 doesn't tell me I have 2 irons, right? The 2 is the name of that ion because it has a 2 plus and a 3 plus. So the 2 is there to tell us that this is the iron with a 2 plus. So why don't we do one with an iron with the 3 plus? So let me use the iron 3 this time. So it's called iron Roman numeral 3. And I'm going to do it with phosphate, which is PO4 3 negative. All right, now remember, this part, when we're putting it together, the PO4 is not the important part. The PO4, we have to include it. I'm not getting rid of it, but when I'm trying to figure out what the charges are going to do, I look at the charges. Now, if you jump right in and don't think about it, and you just jump right into the crossover, remember the crossover shortcut is really only helpful when the 2 charges are different. But when you have the same charges, do you remember from that first slide? If the numbers on the charge are the same, no matter what we're doing, you only need 1 of each. Okay, so the crossover, what we've been practicing in a couple examples, is when the 2 charges are different. And so we have to figure out how many we need to make those charges equal the same positive and negative. But when the 2 charges have the same number, they already equal the same positive and negative. And so we only need 1 of each of these. So I need 1 iron 3, so that would be Fe, and 1 phosphate, which is PO4. Now notice, when you only need 1 polyatomic ion, there are no parentheses. So this, even though this is how our brain might think about it, is not correct. No parentheses. Now to name this, we just name the 2 ions. So it's an iron 3 with a phosphate. Now, I will tell you, let's say you're working in haste. You're trying to get it done, and you do the crossover. So you look and you say phosphate has 3, so there's 3 irons, and the iron has 3, so there's 3 phosphates. Okay, this is incorrect. But what I want to tell you is, if you ever notice that you have subscripts that can be reduced, like in this case, they could both be divided by 3, then you would do that. So you still might be able to catch yourself if you're thinking about it. The formulas are in the simplest ratio, meaning they're the lowest numbers. So if you wrote the formula, you thought about it in crossover because you're trying to work fast, and then you wrote it down and you're like, hey, wait, 3 can divide by itself, then you would reduce it. So normally we don't have to do that when we do the crossover, but if you missed that the positive and negative charge were the same, and so you tried to do the crossover when they're the same and it's only 1-to-1, you still might be able to catch yourself. So let me do one more. And let me think. Oh, I'm trying to think of another one of the ones we have on our table. I feel like we have a chromium 2+ and a chromium 3+. Oh, no, I want to do copper because it has a 1. Let's do copper. Copper has a 1+ and a 2+. So this one, if you have a 1+, would be copper with a 1. Because copper has 2 different charges. Let me say again, and I know I'm repetitive, but I know where students make mistakes. The ion will only have a Roman numeral if it's one of the ones that has 2 cations. None of the others that we're working with, none of the main group, and some of the transition metals, if they only have 1 cation that they can make, they do not have a Roman numeral. So like calcium, which is in group 2A, is a 2+ only. It would never have a Roman numeral in its name. But things like iron, that can be a 2 or a 3+, and copper, that can be a 1+ or a 2+, they get Roman numerals. So copper can be a 1 or a 2. So if it's a 1+, its name is copper 1. And then I want to put it with sulfate. So sulfate is SO4 2-, and it has the name sulfate, which that's a memorizing thing. Most polyatomic ions end in ATE or ITE. Most do, if you look at their names. There are 2 common ones that end in IDE. There's cyanide and hydroxide. So those 2 do have IDE, just like the nonmetals. But most of the time, if you see an it's true, if you see an ATE or an ITE at the end of the name, that's a polyatomic ion. And you can just look at this chart and kind of verify that for yourself. All right, so remember, when we're doing polyatomic ions, this part is not what we look at first. We would think to ourselves, okay, copper, look over here, I need 2 of them. Okay, and then for the sulfate, this is the whole thing. And I look here, and there's a 1 there, so I just need 1. Oh, there's not a 1 there, it's implied. When I only need 1 polyatomic ion, I do not use parentheses. And so that would be the formula. And then the name is just the 2 ions, so I have a copper 1 ion with a sulfate ion. Now, remember, there are 2 copper ions because we're balancing the charge, but the name is copper 1. The Roman numeral does not tell you how many there are. It's telling you the charge. Okay, so this is not an easy thing. It does take practice, but hopefully this will get you started. You can continue practicing using your worksheet, using your homework, or looking into the textbook. They also have more examples and practice problems to do. Now I'm going to end this specific video and create a second video where we'll go from the name of the compound to the formula. So that practice will be in a second video.